Cool. So today we are very lucky to have Ronak Soni here from Cambridge, though as you probably noticed, he's been visiting us for a while. He's going to tell us about extremality as a consistency condition. Take it away, Ronak.
Thank you. Thanks for the invitation to speak, and thanks for having me around all these months. It's been very great. So this talk is based on this paper I wrote last month. In March. It was last month yesterday. So let me start with some motivation. Some very broad motivation, right? As you all know, gravity has diffeomorphism case invariance. That means that diffeomorphisms are not only a symmetry, they literally must not change anything. So, from the perspective of subregions and entropies, this means two things. First of all, it's hard to locate subregions. You can't just say, okay, here's a coordinate system, here's a coordinate location for your subregion, because someone can come and change the coordinate. But in this, I spent a lot of time thinking this was an important issue, but over time I decided this is not the important issue because you can always define things relationally. You can say, look, the corner of that corner there is a fixed point, and now I just define everything with respect to that. Okay. The more important issue, I think, is that there are these diffeomorphism gauge invariance gives you diffeomorphism constraints. Okay, and because of these constraints, things can be related. Things very far away can be related in unexpected ways. This is what the holographic principle in some sense is about. And so, because of this, it is hard to check whether your subregion, which you define relationally, has a subsystem. Okay. What is a subsystem? Well, a subsystem is something like a lab, where you can push, which in some sense is isolated from the rest of the world. Okay. What aspects of, I have a lab here, maybe some operators in the lab are actually related to some other operator outside. I have to start worrying about that. Okay. But, in some sense, we do have subsystems. Labs exist. Cold atom systems are things where I can do things. So it is interesting to elucidate how this works. How diffeomorphism constraints are consistent with the existence of subsystems. What the word subsystem even means, and so just like you get it all down in mathematical language where I know what I'm talking about. Okay. Now I won't answer this question when I will come to it. So let me come to a narrow motivation. The clearest example of a subsystem in gravity that we know is the entanglement wedge. Okay, in ADS-CFT, if you have a state capital psi and a subregion of your boundary CFT, which is capital B, there is a bulk region typically dual to it, which is called the entanglement wedge. And the duality means that effective field theory operators in the entanglement wedge can be reconstructed in the boundary subregion. And we know that the entanglement wedge is related to is bounded by the minimal quantity to the surface, and so on. And this is quite important because recent progress of black hole information paradox done by people in this very department follows from essentially from just being less dogmatic about what sorts of things can be entanglement wedges. Okay. Something a bit unsatisfactory about all of this, even though it's kind of an amazing amount of progress that has happened in the last 10 years or so, is that all of it in some sense uses replica path integrators. Like to find the entanglement wedge, we first look for the QES formula for the entanglement using the replica path integral. And there is something a bit mysterious about it. It doesn't tell you why this is a good subregion. It just tells you that this is a good subregion. So it would be nice to understand this in a sort of more Lorentzian or Hamiltonian formalism. Okay. First of all, I think it's just nice to have. I just think it's a nice new perspective to approach questions with. Second of all, this reformulating the rules from a replica path integral to something else might let us give us access to new types of subsystems that are harder to see from the replica side. This is again something that Raphael and just been thinking about. I should say that this paper here is my most Berkeley paper yet. So I'm very happy about yeah. So the basic, I won't even, I think, say that much about narrow motivation. Let me tell you what I will change. Okay. The basic point is that there is a potential tension between subregion duality and boundary causality. Okay. So here's the boundaries are subregion capital B and complementary boundary subregion capital B bar. Okay. And suppose someone comes and tells you little b is the subregion dual to capital B. Okay. Now, just by consistency, we know that the causal wedge of capital B has to be inside little b, and the causal wedge of capital B bar has to be space like little b. Why is this? Because operators in capital B and capital B bar just manifestly exactly commute, so the causal structure of the bulk should go. Okay, but then this is all fine. This is in one state. The problem is that it is, you could act with some operator u prime that is localized entirely in little b bar, so it commutes with everything in little b. Okay, such that after the back reaction changes the relative location of the capital B bar and the boundary of little b, and it changes it so that capital B bar now is in causal contact with some portion of little b. This is in principle possible. There is no just given capital B and little b, there is no obvious obstacle to doing this. Okay, and this is not something I'm just like picking up out of nowhere. There are examples in the literature where little b bar here is the same as the causal wedge of capital B bar. This green thing is the causal wedge, by the way. It's a set of points causally related to capital B bar. Okay, this was first I think noticed by Alberi, Mahajan and Marcella, and then Adam Levine, Arvind and I took our hint from here and generalized it a little bit, and then Engelhardt, Jeff and Arvind generalized it a bit further. Okay, but all of this was a particular case of choice of little b bar and therefore okay. So I will extend this work a bit. What I will argue is that in JT gravity plus CFT, it is very easy to create this issue. Okay? To the extent that you can basically create this issue anytime the boundary of little b is not a quantum field.
U prime is locality small b bar.
Yeah, yes.
So that means it exactly commute with b.
Yeah.
Big b.
Yeah.
Okay. So when I think U prime to operate in b bar,
Yeah.
big b bar.
Yeah.
Okay. And then how come that can be?
This is telling you that U prime is not genuinely like you. This is telling you that if you can do this, little b cannot be the entanglement with the capital B. For the reason
Are you assuming here that little b and little b bar are both contain the respective causal wedges? So it's a situation where you're dialing it away from the quantum extremal surface.
Yeah.
Saying in those situations you can get this kind of paradox.
Exactly. That's it.
So the B bar is not in the causal wedge of B.
The causal wedge of capital B. I should have all my other diagrams have
I think the idea is that the original B bar contains the causal wedge of big B bar.
Yeah.
And then you change something and now it no longer contains the causal wedge of big B bar.
Yeah.
B bars.
Yeah.
So it can be in the entanglement wedge of B or large B, even though it's outside its causal wedge. Is that the deal? Not being in the causal wedge of B bar, it doesn't necessarily, it's not necessarily part of the entanglement wedge of B bar.
Sorry, what?
I'm just saying, from what Rafael was saying, it sounds like little b bar is outside the causal wedge of small b bar.
It contains it.
And so,
in the original state it contains it, and then I create a new state with a unitary acting only a little b bar. Sorry, I should change the diagrams are very incomplete. Sometimes the back reaction pushes capital B bar outside.
okay, so then is later on part of the small b bar is now in the entanglement wedge of B.
Yeah.
Okay.
Wait. So part of little b is now in causal contact with capital B bar. So the entanglement wedge of capital B has shrunk. Okay, if this was a little the actual entanglement. In actuality, this should not be possible because this should commute, U prime should commute to the region. Okay? And therefore, if you can do this, little b is not a good candidate for your entanglement question. Okay?
So you say you start by saying suppose B is equal to the subregion dual to this, and then say a priori it's possible, and then say examples were found. It's not like examples were found in a situation where little b is the subregion dual to capital.
Yeah, so this is the point. Sorry, maybe I wrote this slide down. I'm saying that if little b was the bulk subregion dual to capital B, this will not be possible. This will not be possible.
Yeah.
Oh, okay.
But for an arbitrary little b, this is possible. Okay, so now we can ask when is this possible, when is this not possible? And I will argue that it is basically possible whenever little b is not an extremal function. Okay, so basically consistency of subregion duality just tells you that you only look at extremal values. Okay, there are some assumptions involved which we'll get into, but I still think it's a very promising idea. Thank you for the questions. This was helpful. So the notation, all bulk quantities are small letters, all boundary quantities are big letters. So little b, capital B for some reason, little curly a, capital curly A for algebras, little psi, capital psi. Yes, you get it. Anytime you see a small letter, it's a bulk quantity, and then you see a capital letter, boundary quantity. This big bar here is a complement of subregion. And a prime on an algebra is the commutant of the algebra, it's a set of operators that commute with the algebra. Okay. And the duality, ADS-CFT is a duality between a boundary state capital psi and a set of two things, a bulk metric G underscore capital psi and a bulk EFT state little psi. Okay. I call causal wedges W wedge underscore causal. Yeah. So, let me start with the introduction to subregion duality. A reminder for multiple orders. Okay. So, as you know, in ADS-CFT, the boundary CFT is dual to quantum gravity in the bulk. No one knows what the statement means, but everyone says it. So, in particular, believe that there should be a map between states in both vertices. Okay. Now, the plane of semi-classical states of the bulk is not all CFT states. It is actually a code surface of the boundary of the set of boundary states. Okay, the code surface basically built from EFT operators acting on the CFT state, the capital psi. Okay, and subregion duality asks, okay, perhaps a boundary subregion B is dual to a bulk subregion little b. Okay, and we will call the bulk subregion dual the entanglement wedge. This is a bit ahistorical. The entanglement wedge was originally defined by its location and then proved to be the subregion dual. I will define it as a subregion dual and will look for its location. This flip is also something that Berkeley is responsible for. So all of this can be understood through the lens of quantum verification, which says that information in the entanglement wedge is protected against the erasure of the complement of B, or in other words, operators in the entanglement wedge can be reconstructed in capital B. Okay. The specific version of this subregion duality I want to use, the idea of reconstruction I want to use is what's called state-specific reconstruction. Okay, and this is it took me a while to figure this out because most ways of thinking about reconstruction are not good for handling back reaction along the way. Okay, but state-specific reconstruction is. So what is state-specific reconstruction? It says that an operator little u in the bulk can be state-specifically reconstructed. Your little u acting on the state capital psi is approximately the same as the capital U acting on the state capital psi. Okay. For people used to the QAC literature, you expect a holographic map here, which I did not put. Holographic map here that I did not put, but I will not be putting it in this talk. So state-specific reconstruction is just saying that you can mock up the action of the bulk unitary by a boundary unitary on a single state. Why is this useful for backnet? So, unlike in most of your quantum verification literature, we do not demand that the reconstructible operators form an algebra. This is important because I take any unitary U, which creates a nice little smooth bump, acted order 1 over g Newton times. It creates a very, very bad bump which might become a black hole. So really, there are no exact sub-algebras in the bump. So if you really want to keep track of back reaction in your formalism, you don't want to think of your reconstructible operator as algebra. Okay? So secondly, we allow for different reconstruction for different states. So suppose
I ask a quick question about it.
Yeah.
The first reference, you mean the paper by Jeff and Chris that dealt with not the min-max entanglement wedges, but actual reconstruction. I mean, generalizing Harlow's work. Is that what you're talking about?
Yeah. So I am talking about first the one that they introduced min and max CWs and the time reflection symmetric case, and then the
Oh, so you are talking about the min and max.
Yeah. But like
because those are not, I wouldn't.
Yeah. But well, I specifically I'm going to use my max CWs for the work for later. But right now I'm just saying that the notion of state specific reconstruction is quite important. Yeah. Which at least I learned from there because maybe
I'm confused what these papers have to do with that. But,
at least for me, they introduced this idea to me.
I think that was the other paper, the one Rafael was referring to, that there is state specific, right?
Yeah, okay, that's a 2021 paper.
they roll a couple papers, but yeah.
Yeah, I'm just
I don't think the Emacs distinction has anything to do with it.
That's true, it does not. It does not. I didn't mean to play with it. So I think of these three papers as like a unit. So yeah. So hey, the reason that the main reason that the state specific reconstruction is good for back reaction is consider two states, psi and psi with the action of some bulk unitary u tilde. Okay? And due to the back reaction of u tilde, okay, the geometry changes a little bit. So the meaning of little u also might change a little bit. And then the reconstruction might be slightly different in u and u tilde in these two states. Okay? So state specific reconstruction is kind of the right language for reconstruction with back reaction. Okay? I'm not sure the best language, but it's the best language I've found. Yeah. So in the context of state specific reconstruction, there's the definition of subregion duality as follows. So consider a pure boundary state on capital B union capital B bar. Okay. So the max EW of B in the state space, capital psi, okay, is the largest bulk subregion with a certain property. For simple local unitaries in the algebra of the max EW, okay, simple local unitaries in the algebra of max EW can be state specifically reconstructed on the state capital psi. But further, it can also be state specifically reconstructed on capital psi acted upon by any unitary u prime in the commutant of the algebra of the maximum. Okay. This is often said. Another way to say this is that stuff in the max EW can be reconstructed without any knowledge of what's happening in the on the other side, because little u prime can scramble whatever is happening on the other side. Okay. And it's important that it's the same reconstruction for all u primes. This is one of those fun math stuff where putting their existence for all in the right order is important. Now, what does simple mean? In the above papers, simple meant product unitaries on a discrete code subspace. Okay, but like we don't have a discrete code subspace, we don't like know what product unitaries are. So I will kind of fudge this concept to low energy local bulk unitaries. Bulk unitaries that have support in a small region. Okay, so low energy local bulk unitaries in the max EW should be possible to reconstruct them in the state specific manner. Okay, now we know even though I introduced the word max EW, I won't actually use the full weight of that concept. I will just use EW. I will assume min EW plus max EW. So we know that the entanglement wedge is given. The way the entanglement wedge, the location of the entanglement wedge was derived was first by calculating the entanglement entropy of the boundary theory. And as anyone in this room probably knows, it's given by the QES formula, which is the minimal, extremal, it's a surface where the generalized entropy is extremal, and one among them is the minimal generalized entropy, the minimal extremal surface. Sorry. Okay. And remember, I am putting this formula here just to remind you that there's a minimization, there's an extremization, and there are two different steps. Okay. So, to go from the QES formula to subregion duality was done by various people. The paper I want to refer to right now is Harvard's paper in 2016, where they showed that basically in general quantum mechanical codes, subregion duality is required into a QES-like formula. The application of this paper to ADS here typically begins with a path integral proof of the QES formula. A notable exceptions here. But you know, the question I am after really is, can we do everything just using quantum interactions here without ever appealing to a path integral? Assuming only that subregion duality exists in some form. The fact that there is some amount of subregion duality is clear from just causal wedge reconstruction also. You don't need any path integral for that. Okay. One problem is that in gravity, unlike in the paper above, you don't know the bulk subregion a priori. Okay. This issue was lifted a little bit in this paper by Berkeley and Pennington, where they lifted this, but then they found that the actual port subregion was the subregion of the minimal entropy, not the minimal extremal entropy, the minimal entropy. Okay. So it's not. It seems a bit hard for QEC analysis to give us extremality. Okay? And what I want to suggest today is that in kind of using these sorts of results, perhaps gravity can give us extremality and QEC can give us the min. You know? And yeah, that's kind of what I want to suggest. So now I'll get into the real meat, which is explaining my consistency condition in more detail. I'll just pause for questions if you want to ask me.
You just show that slide one more time, the previous slide.
Yeah.
And now let Arvin ask his question or let's hear it.
Like you mean like mean among the extremals?
Yes.
Not the local.
Yes, exactly. Sorry, yes. Take it. So like the discrete code circle of these guys, I kind of want to suggest that it's like each discrete bit is like the region between two extremal surfaces.
Can you remind me about this paper by Parikar?
They used entanglement perturbation theory to, so you know, in the case when there is a human symmetry in the state, like a sphere in a safety or something, you can basically prove Cassini-Vaitham has proved basically prove subregion duality in a fairly strict way, just for the reconstruction. And they basically used entanglement perturbation theory to argue that basically the same subregion but any state, it's always the entanglement with the subregion. Yeah, but they did not use the gravitational path integral. They didn't use the gravitational path integral as an important step. They used only the boundary path integral. Okay. So now let me introduce my consistency condition. Around half to 3/4 of the room has understood it already, but let me go through it slowly. So it's based on this thing called causal wedge inclusion that was discussed in like 10 to 12 years ago. I think I was in school back then. I was in college. Okay. So basic point is that causal inclusion. It says basically that if you have the entanglement wedge of capital B, it better contain the causal wedge of capital B, and or better be space-like separated to the causal wedge of capital B. The reason is that basically any operator here can easily be reconstructed in capital B, and similarly here for capital B. Right? And so basically, like this has to be basically they have to be inside. The causal wedge has to be inside the integrated wedge. That's why it's called causal wedge. I kind of want to extend this to something I call complementary causal wedge exclusion. Okay? Okay, it says that for any unitary U prime localized in the complement of the entanglement wedge, so this is my little unitary U prime, which should have been there in my earlier slide as well, I apologize. Okay, this unitary U prime can in principle expand the entanglement wedge, but it should not shrink the entanglement wedge. Okay? There are reasonable examples where it does expand it, so that is important. But whatever it be, when you take into account the backlash of U prime, the entanglement wedge can be expanded. But in the new state, also causal wedge inclusion must be true. In particular, the causal wedge of B bar after backlashing must be space-like separated to the original entanglement wedge. So, the entanglement wedge excludes not only the causal wedge but also its orbit under unitary is localized in the complement. Yeah. So CCW is basically almost a restatement of the max CW condition. Okay, with two assumptions. First assumption is that there are reconstructible unitaries U which support arbitrary close to the boundary. So dose slash is going to be the boundary point like here. Dose slash is the boundary excluding the asymptotic boundary. Anyway. So yeah, there should be reconstructible unitaries U will support arbitrarily close to the close slash of the entanglement wedge. You kind of expected this to be true, but the definition of max CW did not tell you which unitaries are reconstructed. Just told you some unitaries are reconstructed. Okay. So I'm just putting this in an assumption, but it's not really a major assumption.
Since you're discussing max and min EW, that's like, the idea that the two entanglement wedges actually meet.
No, this is
the
complement of entanglement wedge, not WEP parts.
So you think, which one are you thinking of as a max entanglement wedge?
WEP is the max entanglement wedge.
Yeah. So the other one is the min entanglement wedge of the complement.
Yeah.
Oh.
Yeah, sure. That's it. But anyway, like when I get to the main argument, I'll assume complementary recovery and not worry about the certainty very much. But at this stage, I think, I'm just saying things in the sort of logical order. The other strategy, the other thing that
Why not guarantee the definition of max CW? Max CW is really operator.
it tells you that there are unitaries. It is a maximum region such that by the definition of max CW, it is possible that there are all the reconstructible unitaries are in some subregion here. But if U prime kind of leaks into this part, then reconstruction is broken. This is just like, this is pedantic.
But this is U prime, which is within this W bar. Right?
Yeah.
And you're talking about U in the next slide, which is within WE.
Yeah. But I'm saying that not every unitary in WE is reconstructed. It's actually quite important. So in particular, there's like if there is an external surface here, there's a unitary which makes the generalized entropy of this external surface less than that one. Okay, and then that probably can't be reconstructed in capital. So there are not every unitary in this region can be reconstructed. It just tells you there are unitaries. Yeah, it's just a bit pedantic. Yeah. So the other important thing is that in the definition of the max CW, we used the commutant of the algebra of WE, In CCWE, I used the algebra of the complement of W. Okay. And the point is that you have to expect the commutant of the algebra to contain the algebra of the complement. Because clearly, like everything here is space-like substitute from here, so everything here should come into stuff. And that is basically true. I won't tell you that causality is broken. But it's a bit subtle. It's a bit subtle. And the reason it's a bit subtle has to do with dressing. Okay? When you say U prime is inside the algebra of the complement, you have to be a bit careful that the dressing of U prime is also localized in the complement. The gravitational dressing. Otherwise, the dressing could fail to commute with something in W. Okay? And this can get quite confusing because suppose your U prime is a product of two units, U1 prime and U2 prime. Okay? You made sure that U2 prime was on the complement. So U2 prime acts on your E cap or your state capital psi. It changes the geometry. Now, it might be that U1 prime leaks into W. So you have to be careful about this sort of gravitational spreading also. Okay? And this can get very subtle to check. You have to start worrying about exactly what order of perturbation theory you are at. And I once spent a few months, I think 2 to 3 months with Arvind and Adam worrying about things like this. So while a possible dressing is to just dress all of these unitaries. Okay. To this surface, you just say, okay, whenever I act, it is at a fixed distance to the right of this surface. Okay, and then it's basically you imagine now it's guaranteed to be in the complement. But well, it turns out that this is a very subtle statement, and I will refer to this point again. I will just assume that there is some dressing that keeps U prime in the complement, but I just want to warn you that it's a subtle, very subtle. Okay, so now let me get into the ingredients for the argument. Any questions about this consistency condition stuff? So, the first ingredient is jetty gravity. Jetty gravity is a 2D theory of gravity with two gravitational fields, the metric and the dilettone. Okay, dilettone is a scalar, but it's useful to think of it as a gravitational field. Okay, there is a boundary condition that on the boundary the dilettone is phi r over epsilon, where epsilon is a small number, and phi r is like 1 over g Newton. So we have jetty gravity plus a CFT. The CFT importantly couples only to the metric, so it will not see anything about what the dilettone is doing. Okay. And I will work in the limit where g Newton is much less than c g Newton is much less than 1. This basically is a good limit where you can ignore the fluctuations of the gravitational factor while keeping the fluctuations of the CFT factor, where c is the central time of the CFT. Okay. So the dilettone equation of motion sets R to be minus 2 everywhere. Okay, and so all the solutions are locally reduced to. So you can basically fix gauge, and it's useful to fix this sort of crustal type gauge with the funny aspect that we have two null coordinates, but one of those null coordinates increases towards the function. Okay, this is good for studying 2D CFTs in that, I think. Yeah. And the boundaries are given at WW bar equals 1, okay, where the denominator goes up. This gauge has a residual SN2C symmetry, and I can use the SN2C symmetry to take any point W, W bar and give it the coordinate location 0, 0. Okay, I will keep using this SN2C approach. The metric is kind of fixed. The dilettone is completely dynamical, so that's where everything interesting happens. But since the bulk CFT only couples to the metric, it does not see the dynamic. So it's sort of a very, it's a situation where back reaction is very easy to take into account. Okay. And finally, in this gauge, everything, a lot of the interesting stuff happens because of this boundary condition. Okay, so you basically locate the boundary by this boundary condition. Find the coordinate location of the boundary by this boundary condition. So the coordinate location of the boundary is a bit dynamic. So that if you have a shock, it can kind of create a little kink in your boundary and make the entire right boundary small or better left. Okay. The 2D CFT does not see all of this story, whatever the dilettante is doing where the boundaries are. Okay. It does not even see the denominator in the metric. It only sees the metric EW equals to R because CFT has binary elements. So it's basically a flat metric on like between two hyperbolas. And this manifold has a boost symmetry, which I drawn as two arrows. And there is a vacuum state with a little omega which is invariant in this boost. Okay. And the density matrix of this, so if this right region here is little b bar, the reduced density matrix of the vacuum for the right for that region generates the one-sided boost. It boosts the right half, leaving the left half unchanged. And this is a very bad operator because what it does is it does a relative boost on all the UV fluctuations near the corner, near the center. Okay, so it creates an infinite amount of energy. But there is a good unity for the convex second. It depends on two states. One state will be omega, one state will be psi. Psi is going to be the actual state of our pulse CFT. Okay, omega is going to be an observation. Okay, it is some product of the two density matrices. The details are not important. What's important is that it boosts expectation values. So the expectation value of O in the state with where US prime acts, okay, is the same as the boosted expectation value of O in the original state. E to the delta S here is the change in coordinates is the boost, e to the delta S is the boost rate. So O can have some boost rate, so you get some t factors like this. Okay. Now another important thing is going to be that I have some coordinate location W0, W0 bar. I throw in null ray from it. Does it hit the boundary or does it not? I need to know. How do I find this? The way I find this is basically I look at the expansion, which is the derivative of phi. So from now on, anytime you see a thing that should have an index and doesn't, that index is W. If the thing has a bar, the index is W bar. Okay, this is again 2D CFT equation. As you evolve along the null ray, if the expansion limits to a positive value, then you hit the boundary because the boundary is the region where phi goes to plus infinity. If it limits to a negative value, you miss the boundary because the non-boundary part is the region where phi goes to minus infinity. Okay. Yeah. So and particularly you can actually write down an equation. So again, use the residual symmetry to set this point to 0, 0. And then you can take the right of the equation which relates the derivative of the expansion to the WW component of the stress tensor to say that the expansion at W equals infinity, W bar equals 0 is the same, is related to the expansion at 0 over the original point minus the half average signal energy. Okay, this is the integral of the stress tensor from 0 to infinity. Okay. Now this equation can be rewritten in a very nice way.
I'm sorry, can you just go back?
Yeah.
The light ray, where's the position that the light ray starts?
In this example, these two light rays start from different positions. I'm just saying that the way I instead of solving for the entire geometry, what I'm going to do is I'm just going to look at I'm going to fix theta at some point and then calculate theta far away along the line.
Is there a place in the geometry? What's the alternative thing that the light ray can do here other than
You can go to positive value or negative value of 0, which is 0 is the component. Like you can either hit the boundary, you can go to the singularity, which is hyperpolarizability here, or it can go like it. There's a non-generic case where it hits this point. Yeah. So this is going to be important in understanding causal inclusion. We are going to basically take the boundary of our putative entanglement bridge and throw a line and see where it goes. Yeah. So that this equation can be rewritten in a nice way. Okay. So now define the bulk region, which is B bar. Again, it's the right side of the geometry with W bar polygon. Okay. The quantum expansion at the edge of B bar is the sum of the classical expansion and the derivative of the entanglement entropy as you wiggle the edge. Okay. Yeah. And then what I can do is I can go to this equation here, add a derivative of entanglement to this, add and subtract derivative of entanglement to those things. Then the first term becomes a quantum extension at 0, 0. And the second term becomes something known as a quantum half-array. Okay? Or the QANI. And there is an energy condition, like strong subregion tells you that the QANI is positive. This is called the QANIC. This is a thing that ensures quantum focusing. This is basically the thing that was used to prove the generalized second law of relativity.
Quantum focusing is stronger than that.
Yeah, quantum focusing is based on this. Yeah. So, what I'm going to do is that to evaluate causal wedge inclusion for some wedge B bar, I'm just going to calculate the QANI on the future horizon of B, or the fast horizon of B. Okay? Yeah. Our final ingredient is again the quantum cycle flow. And the thing with the quantum cycle flow is that it literally boosts away the QANI. Okay? So imagine a state psi which has some energy flowing through the future horizon of the B bar. That's the T0 W. Okay? What the action of the quantum cycle flow is as follows. It boosts this energy away. It puts the energy further along the horizon. But the stress tensor has a particular boost, so it gets damped. It gets an equal minus x. Further, it adds a little shock here, whose magnitude is proportional to the derivative of the entanglement entropy. Okay? And the factors work out so that the QANI at S, QANI at S is the expectation value in the state QS prime psi, is literally e to the minus s times the QANI at s equals 0. So the CC flow exactly can be thought of as something that boosts away the QANI. And when s goes to infinity, this goes to 0. So this is so QANI was the thing, QANI was the thing that was focusing stuff, sending a light ray into the singularity rather than the boundary. And here we have a little gadget to send the QANI to 0. Okay? So those are the ingredients questions. Okay, so now the main argument. So let me start with the assumptions. So there are a bunch of standard assumptions, the existence of a single semi-classical word geometry. There's a reason I don't write papers with the word theorem. There's a lot of assumptions going in. First assumption is going to be complementary recovery. So I've been talking about using the word max CW a lot. If you didn't know what that means, that's fine. There's a subtlety I'm getting rid of by demanding that the complement of the EW is the EW of the complement. Okay. And this basically makes B and D bar symmetrical in our analysis. The second assumption is CCWE, which is a consistency condition. The reason I call it an assumption is because I needed to take the max CW and add some assumptions to make it true. The third assumption is that the bulk CC flow unitary for the complement of WE, of B, can be drenched so that it actually lives inside the complement of W. Okay? And there was a bit in the middle where I spoke, but it's interesting. That's actually I'm basically getting rid of that assumption. I'm just assuming that there is some risk. Okay. This seems to be true a priori. There's some papers from Berkeley, a lot of urban in them. Okay. Finally, I assume that the entanglement wedge does not contain islands. Basically, the boundary is like one boundary of my space-time, and the entanglement wedge is like has one boundary. So now with these assumptions, suppose someone has a non-extremal Berkeley B.
Why suppose there are no items?
The next section will include islands. Maybe you will see them. Yeah, you need an extra. You need to go beyond the text of the case-specific papers. Suppose someone hands you a non-extremal Berkeley general B and also guarantees you all these assumptions. Then they claim that little b is the entanglement wedge. Here is how it can disprove it. So, now non-extremality means the boundary of little b, there are four null directions. Okay, non-extremality means that at least in one of those four directions the quantum expansion is positive. Non-extremality means that the quantum expansion is not zero. So in one direction it has to be positive. It may be this direction, maybe this direction. I will just take it to be this direction, and the other three cases can be dealt with by symmetry. That symmetry involves exchanging capital B and capital B bar sometimes, so this is why I need complementary. Okay? So I'll just take this situation where B, little b is the left wedge, this quantum expansion is positive, and then for quadrilateral inclusion I'm assuming satisfied. So basically as this null ray goes off, it hits the singularity. So theta naught infinity, the expansion at infinity is negative, and therefore the Quani along this horizon is bigger than the quantum expansion at this point. Okay? Now consider the state with US prime acting on the side. US prime being the CC flow on the little b bar B, which exists and is localized to b bar by assumption. Okay? And by this assumption that it is localized to b bar, nothing the state in little b is completely unaffected by this operator. Okay? So at a point like just a little bit to the past of this, the quantum expansion in the new state is the same as quantum expansion in the old state. So I start with that as a boundary condition and then integrate Raychaudhuri equation up from W equals 0, that is what 0 minus x squared. Okay. Now, as you know, the classical expansion is the quantum expansion minus the quantum. And as I told you, the CC flow pushes away the quantum. So for large enough s, this expansion at infinity becomes positive. That means that this null ray here goes and hits the boundary. Okay? Here I didn't get into it, but we used the codimension to junction condition of angular involved, and that's where the gravitational constraint comes. And so we violate CCW. Okay? Therefore, little b cannot be the entanglement wedge. So one time this case is if theta naught equals 0. Theta naught is 0. The expansion out here limits to not to a positive number but to 0. And so that means that you never the causal wedge never actually comes in causal contact with it. So in the extremal case you are safe. In the non-extremal case, there is always a problem. Okay. So this is the main argument. Let me pause for questions before adding a comment. Does it make sense to people? I have plenty of time, so I can go over it again if anyone wants. Okay. So, one comment is that without, what can you do without the complementary recovery assumption? Without the complementary recovery assumption, all I can say is that basically, all I can say is that the expansion, the quantum expansion here had to be 0 or less than 0. Okay. I use if the quantum expansion here was less than 0, I was using complementary recovery to relabel what capital B and capital B bar were and do the argument along the past present here. But if I don't have complementary recovery, I cannot relabel B and B bar, and so negative quantum expansion is allowed. What that means is that the generation decreases under output deformations of orientation. Okay, these are the consistent. These are the ones that don't follow this consistent condition. Interestingly, this seems kind of opposite to the story of Raphael and Jeff, and I don't know why. Okay, so that is the thing. Let me quickly tell you what happens with islands. I don't want to get into the details of it. But with islands,
So can you just, I didn't quite understand what the statement was. You're, what are you not assuming now that you were assuming before?
complementary recovery. So I cannot really. So now, if I'm talking about max EW of B, I cannot just say, okay, now let me talk about the max EW of B correction. Because the EW.
So earlier you were saying you were considering a candidate surface which was not quantum extremal in the sense that the outward future directed congruence had strictly positive expansion.
Yeah.
Okay, and then you showed that that's a contradiction with the fact that by unitaries acting only on the right, you can actually ensure that it should have negative. Sorry.
That if the outward future directed or outward past directed expansion is positive.
You should have zero expansion.
Yeah, so it should have 0 or negative. The argument I actually went over in this slide.
Can you actually go back to that slide?
Yeah. There's nothing wrong if it's negative. If it's negative, then theta has limit to a negative number. So,
but say that at infinity had better be 0, right?
no, if you hit the singularity, then it's negative.
No. I mean, if it doesn't hit the singularity.
But I'm okay with hitting singularity.
Don't we expect theta at infinity to be 0 for a causal horizon?
No, but I don't want it to be the causal horizon. I'm just saying that
but if it is infinity, isn't it? Oh, I see. You want it to be negative.
Yeah, negative or 0 because I don't want it to hit the boundary. If it hits the physical boundary, then that's fine. But if this guy is negative, then this ray does not hit the physical boundary. Okay. So in that case, what I do is I relabel capital B and capital B bar and point out that the quantum expansion here is the past directed quantum expansion here is positive, and then I run the argument here. But if I don't have symmetry between capital B and B bar, I cannot do this. It's a bit tricky. Like a lot of these points are things that kept me awake.
Sorry, why do you say it's the opposite of what Jeff and Raphael said? Why do you say it's the opposite of what Jeff and Raphael said? Because it seems to me like it's an agreement.
So in Jeff and Raphael's case, whichever regions are not the boundary of the boundary is either extremal or the boundary of A, where the outward where the generalized entropy increases as you go out. Okay. Because basically, otherwise you can just increase, you can just take an outward deformation and decrease in generalized entropy, and that would be more.
I mean, these are entangled wedges of boundary regions, right?
Yeah.
So their edges have to be extreme in our story.
Yeah.
Exactly extreme. So why is that contradict this?
It doesn't. It's not a sharp contradiction. I was just like, I was just weird out that you are allowed cases where generalized entropy increases in the output information, like here you only have cases where it decreases. And I don't know what the difference is.
So, yeah, so even if you say the similar argument goes through in the general case, so it seems like when you have anti-normal wedges, when the expansion is negative, you're fine, right? The argument goes through. So this is like when you only have Emax wedges. And in the definition of Emax, you only use, like, you take union of anti-normal wedges.
Yeah, but the actual Emax is extremal. Actual Emax.
Whenever they don't coincide with the yeah.
Yeah, so like, yeah, in the definition, in the middle you use anti-normal stuff, but in the end, there's a theorem 2 in that particular section of Rafael and Jeff, which is.
Yeah, when the edges don't coincide, yeah.
I looked this up in the morning, so that's good.
I mean, this causality argument fundamentally applies to the complement of the min entanglement. Right?
Yeah.
So that's the one that we're
Yeah. I suspect that the actual connection between this and you guys' work is simply that the definition of subsystem for you actually should allow you to break.
Your citations are confused. Our paper, as much as I love that you cite it, has nothing to do with your work, because this is the place where you should have cited that 4-author paper that is about maximum entanglement wedges off boundary reaches in AES, which is what they're thinking about.
That's right.
You don't need the generality in our paper is about entanglement wedges of arbitrary boundary regions in general space-times.
Yeah, I guess that's fair. Okay. That's fair. Okay. I will tell you very quickly about the case of islands. I'm not particularly happy with it, so I'm just going to tell you who the main ingredient and gloss over it. Okay. So, in the case of islands, I need to make an extra assumption. The assumption is really clear. Okay. I think it's kind of reasonable, but I'm not sure. So, suppose you have some boundary in capital B. It's entangled with two complements. Components. I assume that there is some purification of the state on capital B. The property that every point in the boundary of the entanglement wedge gets its own asymptotic boundary of the complement. Okay, this kind of like this is true in QFT. It's called the split property. It's unclear whether it's true when you take into account gravitational pressures. Okay. So once you make this argument, once you make this thing, once you make this assumption, what you do is you go to this purification and run the argument that from previously over there. Okay. And this is important because here, if you try to run it in the original space time, you just get you don't get any interesting results because there is no sort of boundary for this light ray to hit. Okay. Now I just gave it a boundary for it to hit. It's very in Hindi we call it jugaad. I don't know what a good English word is. It's just very ad hoc. But it's kind of a generalization of the split property to a semi-classical gravity. Okay, so you just assume this and then run the same argument. Again, you have to assume complementary recovery because sometimes you have to purify B, sometimes you have to purify capital B bar, and you can read the paper if you're interested in this. But there seems to be something. Okay, so let me get into a discussion, and this is perhaps the most interesting part of the talk. So, as I mentioned, the CCW, this assumption that the concocycle flow can be dressed to live in complement is kind of almost false. Okay? So, consider an operator A that lives near the boundary of this little b, and an operator A prime that lives inside the causal wedge of B bar, and it's dressed to B. So, the fixed location with respect to B. That's what the little line is. What I just argued is that if this is not an extremal wedge, then the commutator of A and A prime in the state U prime psi is not zero. Okay? But if U prime lives this space, this U prime is spacely separated to little b. Then A and U prime are commute. So you can move these U primes through into the commutator, and now it's a commutator of A and U prime dagger A prime U prime. And a quick calculation shows you that this entire thing is again localized to this particular wedge. In particular, it just moves A prime up from here to there. Okay, and so this commutator should be 0. This is a contradiction, a sharp contradiction. So the point must be that this equality here, this idea that U prime commutes with A, is false unless the wedge is extreme. And as I mentioned, the most natural way to think about U prime is that it's dressed to this point here. So this kind of is pointing to the idea that it's not like dressing to a non-extremal surface is not is inconsistent with constraints. Okay, I have not been able to prove it directly, but I would really love to. I think this might be a very interesting output, like open question to read. Okay. Now you might ask, okay, is this all 2D 3FT, is it called JT gravity, or is there something in higher dimensions? I think in higher dimensions, the broad idea, I went into a lot of detail to make things concrete. The broad point is, I have some wedge. I asked, what purification does this wedge have? Consistent with the gravitational constraints. The point is, if the quantum expansion out is positive, then there is a purification and this Dal rate goes and hits the boundary. Okay? And that's really all I said. I gave you a nice bulk unitary in one particular case which actually does that job. But the broader idea is just that we look upon the set of purifications of the bulk wedge and see whether there's any purification that creates a problem. My suspicion is that that is like the real story, but I can't say it yet because state-specific reconstruction does not allow me to say this. At least as it, or rather the text of the papers that have been written do not allow me to say this, and I suspect there are some additional subtleties. The reason is the state-specific the SSPU reconstruction tells you that we have reconstruction in any state acted on by a bulk unitary component. But to create a random purification, I need a boundary unitary component. Okay? And these are two different concepts. It need not be that this guy implies that. So I am kind of thinking about whether this can be justified in any situation or not. What this means. Okay? Now I will say a few things assuming that all of this works out and there's a high dimensional story. It could be that there is no high dimensional story and everything from here on is not even a problem. Okay? The first interesting output then is that it gives a direct relationship between extremality and focusing. It's a sort of weird fact about the QIS function. You extremize Sj, but Sj is also the thing that focuses. It's the thing whose second derivative is positive along the rings, or negative along the rings. Okay? And this is kind of the thing that makes a lot of stuff. Causal inclusion, entanglement by nesting, all the consistency conditions you can think of. This is sort of the most important ingredient in all. Penrose singularity theorems is also in some sense good things. In particular, this becomes particularly sharp in higher dimensional theories of gravity, where in principle there are many potential choices for the general for example, the JKM communities. And it was noticed again around 10 years ago that the replica positive led to the same choice as demanding focus. She now found the answer, found an entropy from the replica positive, and he said, okay, it has to be the extremal point of some particular functional. And Aaron was asking, okay, what entropy satisfies the second one? And he found the same choice. Okay, and this has been a bit of a beauty. And the point is that this sort of approach can in future make a direct connection between the two. That it had to be, it would be inconsistent if long and word disagree. It would kind of be a satisfying statement. Okay. Finally, let me talk about a potential new derivation of the QES formula. Okay. So Harlow showed that there was an equivalence between the QES formula and subregion subunit formula. So we now have something to say about subregion subunit, right? So let's see what we can say about QES formula. So what I showed was that subregion subunit duality tells you that at leading order in T-Newton, the QES formula, first leading order, is the expectation value of a linear operator plus the bulk entropy. Where this linear operator commutes with operators a little bit. Okay? That's what Harlow showed. Now if you would directly apply this to ADS theory, you get into a few confusions. How do you decide what is little bit? Okay? And that has to do with extremality and minimality, as I said. The second question is, how do you figure out what the area operator is? Okay? So, we found extremality now. I will discuss minimality in the next slide. So now let me tell you how to find the area. It's actually, it's quite fun that I came up with this whole situation, this whole idea for this paper at exactly the right time for me to know the area. Okay? What you can do is you can use the recent time to results. Okay? Let me tell you now. So in the HTML case, using this construction we have, what we've done is we created we have managed to create a future horizon with no energy flux passing through it because we boosted it on. Okay? And this future horizon is now also the future causal horizon. And in exactly these situations, we start to people show that the boundary model Hamiltonian is the area of this plus the bulk model. Okay, and then linearity can let you generalize it to beyond this particular setup. Okay, so this tells you exactly the area of it. Yeah. Finally, minimality, and this is I think me not being able to settle this was the saddest part of this paper. So we now have the area operator, we have that only extremal regions are good. So how do you find minimality of the extremal quantum formula? Now you might think, okay, so Chris and Jeff wrote a paper where they showed in general quantum mechanics course that the actual code subregion is the one with the minimal generation speed. And now, as I suggested, the way I would like to interpret the story is actually that they're minimizing among extremal regions. Okay? But there's a problem, which is that in their story, the area is a number, it's not the expectation value of an operator. Okay? But to have backlight, to deal with backlight action, it is very important for area to be an operator. Okay? I think that there's some work to be done to, like, the work of Nicholas Pennington needs to be extended. In particular, they have counterexamples for simplest extensions you can think of. So it's not entirely straightforward how to extend it. So yeah, this is the end of my talk. Thank you. Any questions?
Any other questions before we finish? Yeah.